today our senior capstone project of 2020. My name is Trent Bennett, and my team members include Ty Jensen and Chris Wolf. Our project is the LiDAR Autonomous Mapping System, which we call LAMS for short. As a brief introduction, the big question is why use these types of systems? Currently, the market demand is projected to be about $4.4 billion by 2023. Many different industries use these types of systems, architectural, engineering, construction industries. One big and important thing with these types of systems is the time and the cost savings. A current 3D laser scanner is in the range of about $5,000 to $80,000. So our motivation, our focus was to build a prototype that could be less than these costs and still be able to do and accomplish the same type of thing, which will be autonomous and in real time. As an overview, the question is, what is LAMS? Our device uses LiDAR technology, which is an acronym for light detection and ranging. You can see on the left-hand side this picture that shows our LiDAR mapping robot. Our project is basically combined into three major components. Number one is the LiDAR mapping robot, which is mounted to the tripod base, which you can see here, with a custom turning mechanism that we use a servo motor to turn the device and to get our 360-degree full range. We also have an embedded system, which actually takes all of that point cloud data that the LiDAR sensor retrieves and stores that into our SD card using the SDHC format. And then we also have a custom 3D modeling software, which we built from scratch, which actually takes that SD card data and converts the file into an object file so that we can then look at it in our 3D viewer tool. As a background to what LiDAR mapping does, or some of the applications that are used in the marketplace, Andrew Tallon, who is a professor at Vassar College, in 2015 actually took a 3D laser scanner, which is this LiDAR type device, and actually scanned and mapped the entire Notre Dame Cathedral. And one big part of that is the fact that the cathedral actually burned down just here recently in 2019. And they're actually using that data and that information to help to rebuild, which is exciting. And that was a big part of our motivation, or a big part of why we did this project. Another application that's used is in architectural studies. They actually use these systems to map the Mayan ruins and different applications like that to produce these 3D models that can be used. To go a little bit further into detail and to talk a little more about our design and the turning mechanism that we created for this system and for this robot. All of the components that were built are custom made in AutoCAD using 3D modeling software, and then 3D printed for the specific parts that we needed. The LiDAR sensor is also, as you can see here in this picture, is turned at 90 degrees for a full 360-degree coverage. On the left, you can see how the servo motor sits in its housing. The servo motor actually turns from 0 to 180 degrees. So as that turns and the LiDAR sensor is continuously turning at 360 degrees, we're getting a full range and we're getting a full map of that entire given space. So that's kind of how this design works and how our robot works.
My name is Ty Jensen and I will be presenting the 3D viewer for the LAMS project. This is the LAMS 3D viewer. We use it to visualize our laser scans, our LiDAR scans. And I'm going to step through the features and show you how it works. So this is the tool menu. We have the two tools. We have the move tool and the select tool. I'll show you the move tool so we can click and drag to move our viewer here. We can also use the arrow keys. We can zoom in and out with the scroll, the wheel on the mouse. We can also use the Q and W keys in order to zoom in and out. We can also change the view settings here. So I can enable these axes. I'll enable them for all views. These are the Y and X axes that we're missing. I also I don't like the grid as much. I like it better without the grid, so I'm going to remove that. I can also change the background to whatever I want. I could do that. I could change these. So I'm going to show a LAM file that we created to test our program here. So it's a sphere that we just created for testing. There's that sphere. We can scroll in and see it closer. This is also customizable. So I can go into the settings here and I can change the point size. We could do 10 points. And we could do a 10 pixel size is what I meant to say. We can also change the color here. Yeah, we can change it to any color we want. We can also, so now I'm going to show the select tool. So we can also, actually before I show the select tool, I'm going to show the full shape here in the wireframe view. So that's what it looks like in the wireframe view. Then we can also show it in the solid view. So here in the solid view, we use face prediction algorithm that we created because we get these points in, but there's no reference to which points make up a face. And so we had to just do we had to interpolate which vertices would make a face. And so we did that using software. Let's go back to the vertex view. So now I'm going to show the select tool and how we use that. So we can just click on a point. And if there's points lined up, we'll get multiple points, but we can separate it out like that, and then we can get better points. We can also hit shift, and we can get a second point. We can delete those points, and we can click and drag as well, delete those points. Yeah, we can edit the point cloud this way. So we can also clear all the objects we have here. That clears all the objects we have. Now I'm going to show an actual LiDAR scan that we did. So what it looks like, we're going to make these points smaller so we can see better. Here we can delete some of this excess. See some points seem to be erroneous, so we can get rid of those. So this was a scan of the inside of a box. You can see the box shape here. Get rid of some of the points around it. So it looks like. So I'm going to clear objects again. Now I'm going to show that we can also import regular object files. So not necessarily just LAM files, but also other files. Going to import an object file. We can import this Airbus here. So we can see that Airbus here that's now loaded in. We could also delete vertices here if we wanted. There we go. It's a large file, so it takes some processing sometimes. And that's that's the LAM viewer.
Hi, my name is Chris Wolf, and I'm going to go over the embedded systems part for the LAMS project. So for our project, we decided to go with the SAM E54 microprocessor, and we went with this option due to the SDHC capabilities. For development purposes, we also used the Explained Pro kit provided by Microchip. Here you can see the block diagram of how we would set up the custom embedded system. And so we decided to use 9 volts for the external power supply, and bringing in 9 volts means that you need to use a voltage regulator in order for us to get our correct voltage sources. And no matter what we would have done, we do need 2 voltage sources here. And so we need a 3.3 volt supply and 5 volts. And so 3.3 volts is for the microprocessor, and then we also need 5 volts provided to the servo and the LiDAR sensor. And so the microprocessor will have communications with the 3 IOs, the SD card, the servo, and the LiDAR sensor, using GPIO ports, SDHC protocols inside of the microprocessor to talk with the SD card, PWM signals sent to the servo to control different angles, PWM signals sent to the LiDAR sensor, as well as UART communications to get data. And here's the customized PCB that we designed. On the left side, we have the power source along with the voltage regulator. So we decided to go with the MAX 20034 voltage regulator. This is a automotive voltage regulator that can handle large voltages and amps provided to embedded systems. The reason we went with this is because the LiDAR and the servo together, they require around 2.5 amps at their maximum. And so that's also why we needed a 4 amp voltage supply. And so given the high amps going through the system, we needed to make sure a voltage regulator would be able to handle this. So we kind of went a little overkill with this, but that's okay. And so in the middle here, we have the micro processor that has the communications to the LiDAR and the servo, as well as the SD card. We also added some extra IO features such as reset button, start button to start the scan feature, as well as 3 LEDs. One is a status LED that the processor will control, and then 2 of them are controlled by the transmission lines of the LiDAR to know when we are sending and when we are receiving. And then above the top pins seen are the programming pins with the capability of being programmed through SWD or a trace function or a trace programmer. So we didn't use a single programmer in case other programming types were needed, though we are using SWD. So that concludes our LAMS presentation. We had a lot of fun making it. We hope you guys enjoyed watching it, and we thank you for taking the time and to watch it. Thanks.